to the 21st episode of the Data Science Decoded podcast. I'm here with Mike. Mike, how are you? How are you feeling?
I'm feeling not bad. Fully recovered from my virus, which I caught a week and a half ago. I took it quite hard, but now I'm okay. I'm already started to work out. So started working out.
Yeah.
And I think we recorded 20 episodes. I think that these episodes can start our season 2. I think 20 episodes per season. It is a quite good thing. I know that seasons sometimes are even shorter, so we can. So I think we can easily start season number 2. So this episode will be episode number 1 and season number 2.
Okay, interesting. We did took 2 weeks because I also wasn't feeling well, and also this week Nir is unavailable, so we took a short break. Yeah, you can think about it as a new season.
Yeah.
And I'm happy that you're back and we are all healthy, and also hope our listeners are feeling well and doing great. And today we have a review paper from 1961, and it's by Marvin Minsky, and he is really famous researcher, right? I think he was at MIT, and he co-founded the Artificial Intelligence Laboratory, and he lived between 1927 to 2016, and he made many great contributions to AI, and I think he's one of the people who coined the term AI, artificial intelligence, around 55. And this paper is from 1961, and it's called Steps Toward Artificial Intelligence. Okay, that's the title of the paper. It's a review paper.
By the way, Daniel, when the term artificial intelligence appeared first, was it in the 40s? Do you know who?
I think it's in the 50s, at least in scientific papers.
Okay.
Maybe there were some books or ideas that are more fiction prior, but in scientific papers it was around 50s, because the first work, and he cites some of the early work, started like at 39, 48, trying to work towards artificial intelligence.
Yeah.
And yeah, that's my thinking. I'm pretty sure it makes sense. And let's read the abstract. And he writes, the problems of heuristic programming, of making computers solve really difficult problems, are divided into 5 areas: search, pattern recognition, learning, planning, and induction. Okay, so he classifies the problems of AI into 5 problems or areas, and he writes, a computer can do in a sense only what it is told to do. But even when we do not know how to solve a certain problem, we may program a machine or computer to search through some large space of solution attempts. Unfortunately, this usually leads to an enormously inefficient process. With pattern recognition techniques, efficiency can often be improved by restricting the application of the machine's methods to appropriate problems. Pattern recognition, together with learning, can be used to exploit generalizations based on accumulated experience, further reducing search. By analyzing the situation using planning methods, we may obtain a fundamental improvement by replacing the given search with a much smaller, more appropriate exploration. And to manage broad classes of problems, machine will need to construct models of their environments using some schema for induction. Wherever appropriate, the discussion is supported by extensive citation of the literature, etc. Okay, so
I think
he summarized this view.
I'm not going to summarize. I'm going to add very small remark. I think in terms of number of citations in this paper, I think in 60s. I think this paper is a survey paper, and it has about several dozens of citation. I think most of the paper we discussed used to have 5-7 citations, but this one is
No,
a different from
7,000. You mean?
no. I mean that
You mean
paper
references at the end?
references at the end, citations. Yeah.
Okay. It's not okay. I thought citations of this paper.
No citation of the papers. The paper which this paper actually
Yeah.
cites.
Okay. The references. Okay.
References. Okay, I just use wrong terminology, right? And in terms of number of references, I think it is the paper with the most references over all the papers we discussed in our 20 last sessions.
Well, it's a review paper, so
yeah.
It makes sense to have a lot of papers.
Yes.
So regarding the abstract, he defined. So in a sense, for him, artificial intelligence or computers, the main problem, as far as I can tell from this abstract, is search. So at the end, you're trying to solve a problem. There's a high dimensional space with all the possible degrees of freedom, and you're trying to go through them in an efficient manner to solve the problem. So at the end, he thinks like search is what machines do, and there are ways to improve it by pattern recognition. So it's some kind of dimensionality reduction or something like that to reduce search, and learning also use prior knowledge to reduce search space. Planning is to break bigger problems to smaller problems. And induction, which is more like building a model, as he said, of the environment, and then try to predict as an AI what's going to happen. So if you have a model of the environment, again, you can also reduce search space because you don't have to go over all the possibilities. So this is his view. Does it make sense to you, Mike? If you think about AI?
It does make sense. I'm wondering about one thing. When we are training our deep neural nets or any type of machine learning model, can it be defined as a search or can it be defined as a learning? Because in order to learn something, we need to choose a model type. It can be transformer, it can be convnet, it can be some Mamba or state space models. It can be some classic machine models. So this choice actually massively reduces the number of search space. From the on the other hand, we are learning. Then by the way, now I understood. When we pick the model type, when we learn which model is the best for our task, so it is learning. So I think this broad categories somehow maybe survive 60 years. So I think that these categories are quite good even now, 65 years later after this paper was published. And I think
I agree. Meaning a lot of it seems similar to how we think about AI. Again, I say AI because it's more general than just machine learning.
Yes.
Meaning, machines or algorithms that could solve problems. And it still sounds similar to today. I think today more of the emphasis is on data, meaning I have a lot of data and how I can leverage that. I guess back in his day, there was less data and there were more heuristics and, some kind of symbolic models, because that's what they had back in the day to play with. But most of the things are similar.
Yeah, but by the way, neurosymbolic models are quite popular right now. There are some companies, and I have a buddy
yeah,
who
for
works
sure.
for a company which
Yeah, yeah.
is to develop some neurosymbolic model together with all these LLMs and some standard models. But neurosymbolic stuff is not dead. In any way, is not dead.
Yeah, that wasn't my claim. My claim was that his paper is paying less attention to data compared to
Yeah,
how we think
yeah,
about it
yeah.
today. And I have some interesting paragraphs highlighted, so I'll read to our listeners. He says at the introduction, I believe that it is that we are on the threshold of an era that will be strongly influenced and quite possibly dominated by intelligent problem solving machines. But our purpose is not to guess about what the future may bring. It's only to try to describe and explain what seems now to be our first steps towards the construction of artificial intelligence.
Very, very
Sounds
interesting.
cool.
Yeah. And remember that this paper was published in 1961 or 1960, 65 years ago. Okay, and they thought that they was in some threshold to the some groundbreaking models, machine learning, even artificial intelligence, thinking machines and stuff like that. And I guess we are a bit closer to this era now in 2024.
Yeah. Again, it's been 64 years, and his sentence sounds like something somebody would say today. With
Yeah.
specifically now OpenAI released O3, that shows to break a lot of benchmarks.
Yeah. Well, there's a lot of buzz around it, but
Mhm.
I'm still not impressed. But it is a separate and very different topic from this paper. I think we'll sometimes make some episode about all this benchmark beating, which are very popular.
Okay, that's a
large
different
language model.
discussion.
Yeah.
Yeah. I just wanted to say that a lot of the concepts that he introduces here are relevant for all three,
Exactly.
actually.
Exactly.
But let's continue. The first chapter is called The Problem of Search. I'll just read the introduction to the chapter. It says, if for a given problem we have a means for checking a proposed solution, then we can solve the problem by testing all possible answers. But this always takes much too long to be of a practical interest. Any device that can reduce this search may be of value. If we can detect relative improvement, then hill climbing may be feasible, but its use requires some structural knowledge of the search space. And unless the structure meets certain conditions, hill climbing may do more harm than good. Okay, so he says again, what's the problem of search? In perfect world, we can run through all the possible solutions, but that will be infinite or close to infinite. So we need to reduce somehow the space. And one of the most promising ideas back in the day is what is calls hill climbing, which is in a sense optimization, some kind of gradient descent optimization techniques. And we reviewed one paper that was one of the first ones. And make sense, Mike?
Yeah, a very small remark. I think here he's referring to not gradient descent, but maybe gradient ascent, because we are not talking about. It looks like he's not talking about the loss function minimization. He's talking about reward maximization. So the purpose is to choose a solution which maximize some reward, which is not always is very well defined. By the way, it hasn't have to be gradient descent. It may be some genetic algorithms. What we are doing in genetic algorithms, we will do some pseudo-random transformation of our solution, of our vector of weights or anything, and when we just evaluate it versus our old solution, if this perturbed solution is capable of achieving better results when we replace the old one by the new one, which is the most basic genetic algorithms. The modern genetic algorithms are much more complicated, but this is a main idea. So it also can be called in some way hill climb.
No, but look,
yeah,
he's talking about hill climbing.
Okay.
And he says here, estimating the gradient for each coordinate. So it's sounds like a gradient descent. And even he talks about the troubles of false peak problem is the chief obstacle to machine learning by this method. So what we call today local minima.
Yeah. And it is not a problem in many cases.
Yeah, but back in the day, there were the beginning of this, right?
Exactly.
And he says even the space is thus composed primarily of flat regions, or they call it messes. Okay, and I don't know, today it's like saddle points or whatever, right?
Yeah. The most appropriate terminology is saddle point for this.
So it's cool that, again, a lot of the things we know today already were introduced to some degree back then.
And here, by the way, he's talking about multivariate optimization, because it's not a very big problem to optimize the function of one or two variables, but when you have a million variables or billion variables or tens of billions of variables, when you encounter all the problems he described in this paragraph.
Yeah, and look what he says in the end. These methods will be arranged in hierarchies, like the search methods, and in even more complex, perhaps recursive structures. And perhaps what amounts to straightforward hill climbing on one level may sometimes appear on a lower level as a sudden jumps of insight, which is an interesting claim.
What does he mean by that?
So he'll mean that like an AI will have a lot of different subsystems who do search or do optimization, like let's say gradient descent, and on different hierarchies of the problem. And some hierarchy will look at the other one, let's say on the higher hierarchy that solve the problem, as having some insight. So like we say today, if you know JGPT, I don't know, output something interesting, we say, oh, it has insight, you know, it solves a problem that is hard. So because we don't know what's happening inside. So it's again similar ideas of,
so
or
it's some
at least
auxiliary system which helps you to solve your problem.
Yeah.
Okay.
And chapter number 2 now. So after search, he talks about the problem of pattern recognition, and I'll read. In order not to try all possibilities, a resourceful machine must classify problem situations into categories associated with the domains of effectiveness of the machine's different methods. These pattern recognition methods must extract the heuristically significant features of the objects in question. The simplest methods simply match the object against standards or prototypes. More powerful properly list methods subject each object to a sequence of tests, each detecting some property or heuristic importance. Then he says these properties have to be invariant under commonly encountered forms of distortion. And then he says two important problems arise here: inventing new useful properties and combining many properties to form a recognition system. For complex problems, such methods will have to be augmented by facilities or for subdividing complex objects and describing the complex relations between the parts. Okay, that was long, but to me, it's similar to, I don't know, like classical machine learning, when you try to learn a classification problem or regression. And he says it's important because you want to reduce the source space and don't go all over possibilities.
Yeah, I guess it is exactly like that. He's talking about, feature engineering or feature construction, which is crucially important in a classic machine learning. In a deep learning, we I can say that we managed to get rid of this manual feature construction. We have our deep neural nets, which are capable of extracting good features, good light and
Good embeddings.
good embeddings, good light and representation of our data. But still, for many times, some problem when the data is not very structured. If the data is structured like audio, video, or images, we don't need to do any feature engineering because this problem more or less is solved. We can just use these representations by deep neural nets like Clip or Lava or stuff like that.
And again, data solved it
Yeah.
for us, right? Because we have so much data, we can train
Yeah. But for
big
classical
models.
problems, tables, some tabular data, we still need to construct to engineer our features, so the problem still stands.
Yeah. And for our listeners, I scrolled a little bit down, still the same chapter, and he gives a lot of examples. But I want to emphasize, he talks about bias nets or various nets for combining independent properties. Okay, so introduces those ideas similar to naive bias classifier. And also he talks about maximum likelihood estimates here. Again, reminds us of our first episode, Fisher and his paper. So it's cool that we have all the important things here.
By the way, I'm not sure he's the first who introduced Bayesian networks.
He's not the first. He's citing those that introduced it.
And he's
Let's
talking
see
about
what
some
he says.
binary, right? He's talking about some binary, Bayesian networks. So then, where each feature has may have only two values, 0 and 1, and
here
yeah,
the references to this.
Yeah, and then and as far as I remember, the objective is to build some graph, or we can call it a Bayesian network, which represents our data in the best way. I don't remember how this best way is defined. Maybe minimization of some sums of of these binary neurons. I don't remember. But still, it is interesting that he mentioned it in this chapter.
Cool. If we continue, and he also cites the work of Rosenblatt, the perceptron, that we also reviewed in one of our episodes.
Yeah. So and he's talking about think about it. He's talking about all this stuff, all this Bayesian network is a part of his pattern recognition. So actually, this he's trying to detect some pattern in your data with the help of this Bayesian network, and then you think about it a bit. Looking for some, for some equilibrium. Maybe I don't remember. I admit it. I don't remember the main principle of this Bayesian network, but still thinking about it as a pattern recognition is quite interesting, because you are trying to implicitly represent the structure of your data by some graph, because the Bayesian network is some type of graph, and it's quite interesting.
Yeah. Again, the idea is to help you reduce search space if you have some kind of a model that can help you.
Yeah.
Okay, chapter number 3, which is defined as learning systems. So again, maybe it's confusing us because we just reviewed pattern recognition, which is mostly what today is called machine learning. Actually, chapter number 3, and I'm going to read it to you, the abstract, the introduction to it, is actually more like reinforcement learning today. So I'll read it to you. In order to solve a new problem, one should first try using a methods similar to those that have worked on similar problems. To implement this basic learning heuristic, one must generalize on past experience. And one way to do this is to use success reinforced decision models. These learning systems are shown to be averaging devices, using devices which learn also which events are associated with reinforcement, i.e., reward. We can build more autonomous secondary reinforcement systems. In applying such methods to complex problems, one encounters a serious difficulty in distributing credit for success of a complex strategy among the many decisions that were involved. This problem can be managed by arranging for local reinforcement of partial goals within a hierarchy, and by grading the training sequence of problems to parallel a process of maturation of the machine's resources. Okay, so again, I'll just reiterate, he's talking here more like a reinforcement learning setup, and the problem that he's raising, if you want to have a reward that you want to emphasize or optimize for, how you break this huge reward at the end to smaller parts that throughout the optimization process you're gonna show the system. So I think that's the problem he's talking at the end. And to our listeners, there's like a plot of environment and reinforcement machine and a response and stimulus and a trainer. So again, similar to reinforcement learning problems that we see also today. Make sense, Mike?
Yeah, this is quite this interesting claim. It claims, I think it may follow from what is written in this summary that this reward function is stems or is built from your past experience. This is the way I understand this paragraph, because this basic learning heuristic. What is basic learning heuristic? It's some way to construct your reward function, and maybe your reward function is constructed based on your past experience. You want to build an autonomous car, and you learn something, then you crash your car off the rock, and if you drive carefully and you don't crash your car off the rock, and also there is quite interesting claim. This can you get back to this paragraph?
Yeah.
These learning systems are shown to be averaging devices.
Yeah.
How do you understand that? What does he mean here in this sentence?
Yeah, so I understand that if you have previous data that you can train the system on, it learns the average of whatever in the signal.
So it is some kind of offline reinforcement learning, and you learn on some the past data. And by the way, at least in some implicit manner, he describes here in this paragraph some sparse rewards, and then you reward the sparse, and you get to the end. It is quite not trivial to understand what decision make you more near to your goal, or throws you far from your goal. And just when you reward the sparse, it is quite untrivial. So, and I guess he's talking about it, and he's quite also it is quite untrivial to understand what out of your decision really neared you to your goal, or maybe throwed you far away from your goal. It is very untrivial, because you are doing a lot of decision during this process. In the case that you reward the sparse, so I think, at least for my understanding, he's talking about stuff like that, all these sparse rewards problems. At least for me.
Yeah, makes sense what you said. And now I looked here he gave some also a little bit of the math behind it. We won't go deep, but it's interesting that he talks here about statistical learning schemas, which again is similar to what we do today with a lot of work I've made in statistical machine learning. So that's cool.
And he also has here exponential averaging.
Yeah.
Which apparently was popular even 65 years ago.
And then again, there's some kind of a figure of environment, the machine, stimulus, response, trainer.
So you
And
have it is quite interesting hymn. Let's take a look at this hymn, Daniel.
At what?
This figure number 9. Let's take a brief look at this figure number 9. You have an environment, and you have here reinforcement machine, and you have the trainer, and you have something which is called U. And it is interesting what are the roles of each. I understand what is an environment, but what is the difference between a reinforcement machine and trainer? Maybe trainer is a machine which
here it says what's U. The device U is not itself a reinforcement learning device. It is more like a Pavlovian conditioning device, treating the signals as unconditioned stimuli and the as signals as conditions. I'm not sure what he means. I think he's taking that from like psychology or neuroscience and some ideas from there.
Okay.
And there he talks about animals. So I think it's more like some kind of high level idea. But here I marked a sentence where he talks about games. So he's saying, let us review very briefly the situation in playing two-person board games of this kind, as noted by Shannon. So he's actually quoting Shannon, but not his paper on Shannon information. But I think the same year or year before the Shannon information paper, Shannon had a paper about playing chess with an algorithm.
Minimax algorithms?
Yeah, so he says, such games are in principle finite, and a best strategy can be found by following out all possible continuation. If he goes here, I can go there, etc. And then backing up or minimaxing for the terminal positions, won, lost, or drawn. But in practice, the full exploration of the resulting colossal move tree is out of the question.
Yeah.
So he says going all over the possible combination and moves is impossible. And here he shows like a tree of decisions that you can do in this game. And it's like, min max or max min.
By the way, I think the modern algorithms and modern machine algorithms of chess algorithms, I think most of them are based on some kind of Monte Carlo research, and this Monte Carlo research, it contains a very little fraction of all possible moves, because it is even for today's machine, which has a enormous amount of compute. Apparently, compared to the amount of compute 65 years ago, still analyzing for each movie, analyzing all the possible movie, I think it is out of question. It may take a lot of time. I don't know the number of these movies, but I guess it is huge. You know, you need
I
to
want to say that
seven moves. You know, I heard sometimes that the greatest grossmeisters think 7 or 8 moves ahead. Now think about a tree which you need to build to the depth of 7 or 8 in a chess, and this tree must include all the moves of your opponents as well. I think it is a
no, but they do it. They do a few, like they can see 7, let's say, moves in the future, but around their area of the board that they're playing. They cannot go over all the possible moves of each possible piece.
Nobody
7
can.
in the future.
You see, apparently it is too much.
No, so what they do heuristics. They know that a lot of the moves they feel are wrong, so they not even think about them. I play chess. I'm not a really strong player, but for amateurs, I'm quite strong, and I've been playing since a young age. So I can think a few moves in the future in chess. But again, like calculating a few moves in the future you like do the relevant moves.
Yes.
Like, right, there's a lot of unrelevant moves, move some piece far away, which you feel and you know that is irrelevant, so you don't think about.
Yeah.
Again, sometimes it's a mistake, right? That's also grandmasters make blunders, but usually you have some kind of heuristic that you feel is right.
Yes. But still, they are not doing some any kind of some brute force search. They are not. They are not checking. They are not evaluating all the possible solutions.
Yeah, they cannot do all the possible, but they can do quite a lot.
Yeah.
Like they do different ideas and can take, some moves can take 10 minutes. Usually a game is 2 hours each person. But my point I wanted to say, it actually is relevant because this chapter is about more like reinforcement learning and research. And you think about like AlphaGo, right? So it's a similar idea. There was a reinforcement learning setup, and it gets, it beat chess, and the ideas are really similar to what he describes here.
Yeah, and by the way, the reward is very sparse here. You get your reward only in the end of the game when you win
Exactly.
or you lose. Yeah.
Exactly. Like how you say if one move is good or bad if only you know it at the end of the game.
I'm pretty sure that in the model chess engine and the Go engines there is some neural net which is
There
given
is, yeah.
function that just computes the value function or some
Yeah.
odds of winning or odds of
Yeah.
lose. Yeah.
Yeah, you can you show her at the end. It's neural network. It gets the image, and then it can give a value. How good is the position? And then you can use that network in order to train another one with reward. And then you can
exactly.
also get reinforcement learning.
And this way you propagate over your over a tree. You are trying to find paths with a maximal reward or with a maximal chance of winning. I'm pretty sure it's much more complicated than that. But the main idea is to choose the path which will give you the highest chance of win. Taking it very simplistic.
Yeah, so let's move to the next chapter, which is number 4, problem solving and planning. And I'll read. The solution by machine of really complex problems will require a variety of administration facilities. During the course of solving a problem, one becomes involved with a large assembly of interrelated subproblems. From this, at each stage, a very few must be chosen for investigation. This decision must be based on 1, estimates of relative difficulties, and 2, estimates of centrality of the different candidates for attention. Following subproblem selection, one must choose methods appropriate to the selected problems. But the really difficult problems, even this step-by-step heuristic for reducing search will fail, and the machine must have resources for analyzing the problem structure in short, for planning. A number of schemas for planning are discussed. Among them are the use of models, analogous, semantic, and abstract. Certain abstract models, character algebras, can be constructed by the machine itself on the basis of experience or analysis. Okay, so he talks here about, as far as I understand, problem solving and planning is the concept of trying to take a big problem and break it into smaller ones and deciding which are the important problems to solve. Again, you have a search space. Where should you focus? Something like that.
Yeah, I guess so. It is.
Makes sense.
It is.
I feel like it's similar to other chapters, but I think the emphasis here is breaking bigger problems into small ones using logic, using some kind of formal logic or various ideas. And he cites a lot of logical papers. He cites Russo and Whitehead, which are famous logicians from the previous century. So this is the chapter more about like logic and maybe similar to here, heuristic for subproblem selection. So here I didn't find anything which is really interesting. So I'm going fast over it for our listeners.
By the way, planning
again, a lot of logic.
Yeah, but planning in a very general term is quite popular in today's reinforcement learning, because sometimes when you know the not physical or mathematical model of your world, you can plan. If you know the model, the world model, you can also plan. And if this model is not too much random, you can plan some good strategy. You don't have to make one move in a moment. You can plan your whole strategy. So he's not talking about it. I'm talking about something very basic, but still this approach of not planning the next move, but planning the whole strategy for many moves ahead. It is very valid and also widely used approach now as well. But he's talking about very tough stuff. I tried to read this chapter, and I failed to understand it.
Because again, to our listeners, there's a lot of logic here and a lot of definition, and it's more like the computer science side of it.
Yeah.
Of machine learning. And we move to our next chapter, which is the last one, induction and models. And here he says, part A, intelligence. In all of this discussion, we have not came to grips with analyzing with anything we can isolate as intelligence. We have discussed only heuristics, shortcuts, classification techniques. Is there something missing? I am confident that sooner or later we will be able to assemble programs of great problem-solving ability from complex combinations of heuristic devices. Multiple optimizer, pattern recognition tricks, planning algebras, recursive administration procedures, and the like. In no one of these will we find the seat of intelligence. Should we ask what intelligence really is? My own view is that this is more of an aesthetic question, or one of a sense of dignity, than a technical matter. To me, intelligence seems to denote little more than the complex of performances which we happen to respect but do not understand. So it is usually with the question of depth in mathematics. Once the proof of a theorem is really understood, its content seems to become trivial. So you got what he's saying?
Yeah, I guess it is a quite powerful paragraph. He states that the question what is intelligence is not well defined. It is a quite ambiguous question, because for him, and I tend to agree with him, by the way, intelligence is how did he define it? Complex
so he said
performances which we happen to respect but do not understand. Yeah, because we as humans solve some problems and we don't fully understand in many cases we don't even close to understand how we are capable of solving these problems. Some basic stuff, many of the people don't understand. I think not many. I think how do we add numbers in our head? Nobody knows how and some basic stuff, we don't understand it. I think it is a very important point, because we're now trying to define and all this AGI and stuff. And why it is so complicated? Because in many cases you can perceive this intelligence, but you can't explain it, and this is the reason we have really hard times to define it, because it is something not all stuff related to our thinking is not immaterial, in material, not material.
Immaterial, yeah.
Immaterial, yeah. But here he's talking he's talking about and he's talking about that it's very hard to define intelligence, and there is very strong sentence at the end. Once the proof of the theorem is really understood, its content seems to become trivial, and it is very important. We are in terms of intelligence, we are, although for example you learn your son to solve some mathematical problem, and then this problem seems very very very, and you invest your time and you sit in and trying to explain it, and it is very tough, but when he understands, it is very simple to him. But if you ask him were you capable of solving this problem, he can't answer you. He can't answer because he doesn't know. Somehow, something happened in your brain which brought you from the state which you were not capable of solving this problem to the state that you are capable of solving this problem. What happened? Nobody knows. And this is, for me, it is the nature of human intelligence. Stuff happens, you are improving, but nobody understands what really happens. If anybody could research our brain prior to the state that you understand how to solve this problem, and after the state, maybe then there are some neurons which are connected. Maybe some random part of neurons which were unconnected, and now they are connected with some connection. But nobody knows, and this is the fluid nature of intelligence. For me, it was long. Too much words.
You in a sense, you agree with him, and I agree with him. It's the exact definition is more aesthetic, meaning some people prefer that, some people prefer this definition. And the second thing he describes in this chapter is inductive inference. Okay? And the idea here is, in order for machines to perform better, or let's say reduce search space, they need to have a model of the environment. And then if they have a model, they can predict what will happen next. This is the inductive inference. And he cites a few works here, and he says there's quite a literature concerning this subject, but we shall discuss only one approach which currently seems to be the most promising. This is what we might call the grammatical induction schemas of Solomonov, that we touched a little bit when we reviewed
Kolmogorov complexity.
Kolmogorov complexity. Exactly. And the idea here is exactly, it talks about the length of the program that you need to write to describe the problem or to solve the problem. So he discusses it here.
But Daniel, Solomonov complexity is not the length of the shortcut problem which you can generate your data. I think it is something a bit more.
No, so it's different. It, for each possible solution to the problem, you take the solution you write the program for the solution and you check how long this problem is, and how compressed or this code that implements the solution, and the solution which is the shortest gets like the highest weight. So you do some kind of Bayesian weighting. So you have still the prior, and then you get data, you update it. The problem with Solomonov induction is that it requires infinite resources and time, because it goes over all possible solutions.
Yeah. So it's a bit more complicated. It is even more complicated than Colmogorov complexity. That nobody can compute, but
it is more complicated
than that.
Yeah. And then it discusses models of oneself. If a creature can answer a question about hypothetical experiment without actually performing that experiment, then the answer must have been obtained from some submachine inside the creature. The output of that submachine, as well as the input, must be coded descriptions of the corresponding external events or event classes. Seen through the pair of encoding and decoding channels, the internal submachine acts like the environment. So again, this reminded me now with ChatGPT, we can ask a question, it answers it. So it has some kind of a world model in order to answer it, right? You can tell it, okay, I can take a cup and I put an egg and something on top, what would happen? Might say it breaks, so it has some kind of a world model. So it's interesting that he talks about it here as well. And I think this is the end. In conclusion, I'll quote his last remark. We have discussed here only work concerned with more or less self-contained problem-solving problems. But as this is written, we are at last beginning to see vigorous activity in the direction of constructed usable time-sharing or multi-programming computing systems. With these systems, it will at last become economical to match human beings in real time with really large machines. This means that we can work toward programming what will be in effect thinking aids. In the years to come, we expect that these man-machine systems will share and perhaps for a time be dominant in our advance towards the development of artificial intelligence.
I think it's just envisioned what is happening more or less now in the last several ages. It took 65 years, and it took 2 AI winters on the way. I think there were 2 AI winters with almost no research about artificial intelligence. Many people thought that this idea is more or less dead. But we are getting there. But the problem is that nobody can tell how we are close and if we are close. Because for me, we are not close to artificial intelligence, which is at the level of human being. And I'm not talking about O3, which is capable of solving complex mathematical problems, but each mathematical problem will cost you $5,000 of computing resources to solve, and it is very unclear how these models are coping with quite simple problems. So, and I suspect that this ability of solving a very complex problem comes on the account of simpler problems which these models will not be capable of solving. This is my impression. I'm not, as I already mentioned at the beginning of our podcast, I'm not impressed about this beating all these benchmarks, and because we don't know how these models were trained, and how the data these models were trained on is close to the benchmark data. But still, in my feeling, we are not very close to the artificial intelligence on the level of human being. And I'm not talking about PhD level. I'm talking about a level of a regular person, average person. And but maybe it will be some breakthrough tomorrow, and I will be forced to tell that I was wrong about it.
Yeah, actually, I just highlighted because he's talking about time sharing multi-programming. So it's like parallelizing compute. So his claim is like soon there'll be machines that could do a lot of computation, in a sense, run through search space much faster, right? And if you're thinking about ChatGPT and now O1 and all this test time test compute, whatever the paradigm is called, when you do a lot of inferences and there's some LLM that decides what's best. So it's exactly what he says in the paper, in a sense, like, okay, we can now search faster because we have better machines in this search space.
Yeah.
And I'm still like, on one hand, he feels, when he writes it in 1961, like soon, in a few years, we'll have this. And today we say soon, in a few years, we'll have it, because now we have all those LLMs. So I'm curious how if we are like him, and in 60 years, somebody reading our papers and will be, saying, oh, interesting insights, but they're 60 years from, so we're really close to something which is, gonna change everything. So to me, this is just an exciting paragraph that tells me that I'm now in interesting times, and I'm excited.
Yeah, for sure. We'll see. I hope we'll see something.
So that's the paper, which is a review paper, and it was quite fun. Any closing remarks on your side, Mike?
No, I think it is a decent beginning of our second season, and I don't think when we ever discussed any solver papers in any of our 20 past episodes. So it is good to start. I think we will discuss more survey papers, but it was a good experience. There are some quite powerful paragraphs. This paper is not very easy reading, and there were some sections which I had troubles, and I admit that I wasn't capable of understanding. But still, you can read some summary. You can ask Sonnet or ChatGPT to summarize it. It's a very popular paper, and I think it has many thousands of citations. So if you are not capable, as me, of comprehending all these quite tough chapters, use ChatGPT to summarize it, ask questions, because this paper is quite important.
Yeah. Thank you for that, Mike. And I would just again summarize that. To me, just made me excited about the time we're living and experiencing all those rapid advancement.
Growth.
Again, might take another 60 years, but who knows? And we're gonna end with that. I wish everyone a great end of year.
Merry
for
Christmas.
those who are celebrating. Yeah.
For those who celebrate, Merry Christmas. Now you must say, for those who celebrate. You can't just tell Merry Christmas. Only for those who celebrate.
Yeah. And those who celebrate Hanukkah, so also enjoy. And I'll see you next time, everyone.
Yeah. Bye.